Good morning to Dr. Arif. We are from Group 3. Today we would like to present about our experiment 4, which is center of pressure. So our group member contain me, Towan Teng, Lok Wei Eng, Muhammad Elmam, and Chung Sun Fu. So for introduction, the pressure center is the point on the summer surface, such as the gates where the free pressure, which is hydrostatic force, acts. For horizontal surface, pressure is symmetrically distributed and acts at the center. For vertical or angle surface, the pressure center lies below the reagent center as the pressure increases with depth. Okay, for objective, the objective is to determine the center of pressure and hydrostatic force due to the water acting on the partially and fully submerged vertical surface, and to determine the relationship between the water height and the moment of the force on the vertical plane surface. So for scope, the experiments masses that we use are 0.05 until 0.5 kg. For theory and working principle, so when the quadrant is immersed, the hydrostatic force is determined as follows. Forces on the curved surface are normal pass through the pivot and cancel out, so producing no torque. So the horizontal force will cancel out each other, and the hydrostatic force on the vertical submerged phase is balanced by the weight and depends on the weight and water depth, and the system is in equilibrium when the moment from the hydrostatic force and the other weight reach mg about the pivot are equal. So the first formula is mg times L is equal to F times Y. So mg is the mass of the weight, G is the gravity, and L is the length of the balance arm, and F is the hydrostatic force, and Y is the distance between the pivot and the center of pressure. For the magnitude of the resultant force, for the resultant hydrostatic force, F applied to an immersed surface is given by this formula. F is equal to PC times A or rho GYCA. So for PC is the pressure of the centroid, and A is the area of immersed surface, and this one is the so the PCA also equal to rho GYCA. So rho is density, G is gravity, and YC is the center of the immersed surface, and A is the area of the immersed surface. So this is the second equation. So the hydrostatic force acting on the vertical face of the quadrant can be calculated as by, so for partially immersed vertical plane can use this formula. F which is hydrostatic force is equal to 1/2 rho GBD squared. So rho is density, G is gravity, and B is the width of the quadrant face, and D is the depth of the water from the base of the quadrant. So for fully immersed vertical plane can use this formula. F is equal to rho GBD times D minus D over 2. So the F is the hydrostatic force. The center of pressure can calculate by using this formula. Yp is equal to Ix over Ayc. So Yp is center of pressure, and Ix is the second moment of area, and A is the area, and Yc is the depth of the centroid. So by use of the parallel axis theorem, which is this formula, F is equal to Ic plus Ac squared, M plus Ayc squared. So for partially immersed vertical plane, can use this formula. Ix is equal to BD cubed over 3. So the B is the width of the quadrant, and D is the depth of the water from the quadrant, and over 3. And for fully immersed vertical plane, can use this formula. Ix is equal to BD. B is the width of the quadrant, and D, the capital D is the height of the quadrant. Then times with D squared over 12 plus small d minus capital D over 2 squared. So the small d is the depth of water and capital D is the height of the quadrant. So these are two diagrams that for the first diagram is the partially submerged quadrant. So the water level is below the quadrant, and the second one is the fully submerged quadrant. So the water level is above the quadrant. The theoretical determination of center pressure. So the depth of the center of pressure below the pivot point can use this formula. Y is equal to Yp plus H minus D. So H is the vertical distance, and D is the depth of the water, and Yp is the center of pressure. So the Y is the depth. So for theoretical result for the partially immersed vertical plane is used by using this formula. The depth is equal to H is the vertical distance between the pivot and the base minus D over 3. So the smaller D is the depth of the water. So for fully immersed vertical rectangular plane, Y is equal to this formula. And the capital D is the height of the quadrant, and small d is the depth of the water from the quadrant, and H is the vertical distance. So for partially immersed vertical plane, can use this formula. Y is equal to 2 ml over rho BD squared. For the fully immersed, can use this formula. Y is equal to ml over rho BD times D minus D over 2.
This meeting is being recorded.
So now I'm going to present our experiment setup. As the figure shown above, this is all the material and the apparatus we are going to use in our experiment. So this device basically works like a beam balance. You add some weight here, and you can know the force acting on the vertical surface of quadrant by apply the concept of balance of the moment. So before we start our experiment, we have to wipe the quadrant with a wet dry to remove the surface tension and prevent the formation of air bubbles. and have to make sure the apparatus is placed on a level surface and adjusting the field heat until the bubble in the split level is centered. And we have to place the knife edge on the balance arm and check whether it can swing freely or not. After that, we attach the right hanger to one end of the balance arm and adjust the counterweight to make the arm horizontally balanced. And we start our experiment by adding 0.05 kg of the right hanger to the other end of the uh, balance arm. And we slowly fill the tank with water until the hydrostatic forces balance the arm, and when each align the arm with the center of marking, we record the water height on the side of the quadrant. Note that if the quadrant is partially submerged, the reading must be recorded in partially submerged data table. If the quadrant is fully submerged, the reading must be recorded in fully submerged data table. Then step 5 until 7 is repeated by adding 0.05 kg of weight each time until reaching 0.5 kg. And we reverse the process by removing the weight progressively and recording the water height. And last, don't forget to drain the water and remove all the wax and clean up any split.
Alright, next, this is the table of depth of emission, the result from the experiment we get. So we get for the loading process, depth of emission, and unloading process for depth of emission. We use unit meter, and we can convert it into meter. So we have partially submerged and fully submerged, and we calculate the average of loading and unloading here. Right, next for discussion 1, calculation of hydrostatic force. For partially immersed vertical plane, we have the equation F equal to 1 over 2 rho g b capital D square. And fully immersed vertical plane, we have F equal to rho g b capital D capital times D minus D capital over 2. The B is width of the quadrant face, D is depth of water from the base of the quadrant, capital D is height of the quadrant face. For mass 0.05 partially submerged with D equal to 0.04 meter, the F equals 0.589 Newton. For mass 0.3 kg, the F is equal to 4.371 Newton. Next, for the calculation of theoretical determination of center of pressure, with partially immersed vertical plane, we have Y equal to H capital minus D over 3, and the other equation is Y equal to formula here we see on the right side. Alright, for partially immersed, for a mass 0.05 kilogram, Y equal to 0.187 meter. And for mass 0.3 kilogram, fully submerged, the Y equal to 0.164 meter. Next, for the calculation of experimental determination of center of pressure with partially immersed vertical plane with Y equal to mgl over F, or equal to 2ml over rho b d square. The fully immersed vertical rectangular plane, Y equal to ml over rho bd times d minus d over 2. For partially immersed or submerged, 0.05 kilogram, I forgot to write the kilogram, Y equal to 0.246 meter. And for mass 0.3 kilogram fully submerged, Y equal to 0.199 meter. Okay, so this is the data table for hydrostatic force and depth of center of pressure. As you can see, we have the hydrostatic force Fn, theoretical depth of center of pressure, and experimental depth of center of pressure in unit M. So we have the partially submerged and fully submerged data.
So now I'm going to discuss about the plot of the graph in our experiment. So the first graph is the graph of hydrostatic force versus the depth of emission. So from the graph above, we can conclude that the relationship between hydrostatic force and average depth of emission is in exponential, which means that the hydrostatic force exponentially increase when the average depth of emission increase. The next graph is the graph of experiment depth of center pressure versus the depth of emission. So from the graph above, we also can conclude that the experiment depth of center pressure is inversely proportional to the average depth of emission, which the experiment depth of center pressure is linearly decreased when the average depth of emission is increasing. So the last graph is the graph of theoretical depth of center pressure versus the depth of emission. So as the graph shown above, we also can conclude that the relation between the theoretical depth of center pressure is inversely proportional to average depth of emission.
So for discussion 3, discuss on the variation of hydrostatic force with the depth of the emission. So according to the table, the depth of emission increases when the hydrostatic force increase with increasing mass. So the depth of emission increase and hydrostatic force also increase. So this explains why it takes more water to get the balance arm back to its initial freely moving position after adding more weight and causing it to descend. So the hydrostatic force therefore rises in the direct proportional to the depth of emission as shown in the graph 1. So despite its initial curve experience, it eventually take on the linear shape. So with equation 3a and 3b, for the 3a is the F is equal to half rho b, rho g b d squared, and F are proportional to d. So F is the hydrostatic force and the small letter d is the depth of the water. So for equation 3b, which is fully submerged, and F is equal to rho b d, rho g b d over d minus d over 2. So the capital D is the height of the quadrant. So F is directly proportional to D. So for the an accurate straight line was plotted in the second half of the graph. So in summary, the hydrostatic force increases with the depth of emission. So in the first half, a curved line is plotted, and the second half, a straight line is plotted. So improvement to the experiment, we should use more precise tool to measure the depth and the force and reduce the friction in the pivot points of the apparatus for accurate center of the pressure result, and test different surface angle, which is the vertical, incline, horizontal, to better understand the pressure distribution.
Okay, for the discussion 4 is discuss on the relationship between the depth of the center pressure and the depth of immersion. The equation HCP equal to HC plus IC over A HC is showing that the relationship between the depth of center pressure and the depth of immersion is linear. So both parts indicate a linear relationship, which is expected because the depth of the center of pressure approach the centroid as depth increase. The second is difference between the experimental and theoretical result. The experimental values are consistently larger, suggesting we having a systematic error in this experiment. And the possible reason for the discrepancy is misalignment of tinting of the quadrant during the experiment, and the no uniform fluid property and unaccounted external force occur in this experiment. For the physical interpretation, as shallow depth, the pressure distributed across the quadrant is moved more uneven, leading to a greater offset between the center of pressure and the centroid. And as the immersion depth increases, the pressure distribution becomes more uniform, reducing this offset. Okay, for the discussion 4 is compare and explain the discrepancy between the experimental and theoretical result for the central pressure. The first is experimental errors, which come from the misalignment of the quadrant, inaccurate measurement of force, depth, or moment, effect of fluid turbulence or parallel error. The second is the theoretical simplification. Assumption of an ideal fluid may cause the problem, and perfectly uniform pressure distribution did not occur, and neglect the surface imperfection in real world case. And the last is trend. It shows that the experiment volume are higher due to greater sensitivity to a light, and a greater that the experimental and theoretical volume converge and the pressure distribution become more uniform. So to reduce the discrepancy, improvement is in alignment, precise measurement, and refine the theoretical model are essential. Okay, for the safety procedure, wearing a lab coat to protect crews from water, and before experiment, checking the condition of apparatus and material used in this experiment, and keep potential water leakage part. For example, in this experiment is the drain valve away from electronic device, and cleaning the experiment site if minor leakage occur immediately. And the last is follow proper experiment procedure to avoid unexpected accident.
Alright, for conclusion, hydrostatic force increases with depth as the depth of emission increases from 0.4 meter to 0.156 meter. The hydrostatic force increases from 0.589 meter to 8.952 meter. The depth of center of pressure shift downward. The center of pressure move lower as the depth of increase. For example, at 0.15 kg mass, it was 0.175 meter, and at 0.50 kg, it reached 0.157 meter. Relationship between depth and force. The hydrostatic force increased proportionally with the depth of emission as predicted by theory. Overall, the result confirmed that water depth affects both hydrostatic force and the center of pressure, aligning with fluid mechanics principle. Next, the experiment demonstrates that the hydrostatic force acting on vertical surface increases linearly with the depth of emission. The center of pressure shifts downward with increasing emission depth, and experimental value closely match the theoretical prediction. For example, at depth of 0.3 meter, the hydrostatic force was 4.371 Newton, and the center of pressure was located at 0.164 meter theoretically and 0.199 meter experimentally.